Welcome to Magnetic Fields Part 5, I'm sorry. Today we're going to be discussing a number of applications of Ampere's law, but what I'd like to do is start out with one that doesn't get discussed very often at the introductory level, and that is how to apply Ampere's law to find magnetic fields for non-uniform current distributions. This is sort of a fun thing to do. What we did last time is we showed you Ampere's law for a uniform current distribution. This time we're going to try it for a case when suppose we have a current density such that the current density is equal to some J naught, a constant, times R for R less than capital R, where capital R is the radius of this long cylinder. And let's say that it's equal to 0 for R greater than R or otherwise. So less than or equal to R, it's J naught R. Greater than, for R greater than R, it's going to be 0. Now, just because the current density is 0 outside the cylinder doesn't mean that the field is going to be 0. As you'll see, it will be a non-zero value. Let's work this problem and see what we get. The difference in this case is, right now we don't know what the effective current is. So if I want to apply Ampere's law, B dot ds is equal to I, let's call it the effective current times U naught. I'm going to draw, in this case, an Amperian loop. Let's look for the case for B for R less than R, so inside the cylinder. So what I would do is draw, let's suppose I want to find it at some point, some distance R from the center. I would draw an Amperian loop that has a radius of R. What I have to do then is figure out how much current is actually passing through this loop when I make this calculation. Now, I know in this case that not all of the current is passing through the loop, but the amount of current changes as R becomes greater up until we reach the surface of the cylinder. So in this case, to find the effective current, what I'm going to do is I'm going to integrate. The effective current will be equal to the integral of J dot dA. So in this case, J is equal to J naught, a constant, times R. My area element for the Amperian loop is just going to be 2 pi R dr. Okay? And so what that does is that gives me a factor of 2 pi R dr, and I'm going to have to integrate from 0 to little r, where little r is the radius of my Amperian loop. And that will tell me how much current is going to pass through that small loop. So I can write this as J naught's a constant, 2 pi is a constant, pull them out of the integral, and I'm integrating from 0 to r squared dr. This is going to give me 2 pi J naught R cubed over 3. So my effective current is going to be 2 pi J naught R cubed over 3. Now I can apply Ampere's law. Go back to Ampere's law. I know that the magnetic field is going to be constant at every point on this loop. It's also in the same direction as ds, and therefore I can write this as B, outside the integral of ds is equal to mu naught times 2 pi J naught R cubed over 3. ds in this case is just going to be 2 pi little r. When I integrate, when I integrate this, I will get B times 2 pi r is equal to mu naught times 2 pi J naught R cubed over 3. Notice my 2 pi's are going to go away, and I'll end up with a magnetic field inside equal to mu naught J naught r squared over 3. So this is for inside the cylinder. Suppose I want to find the field outside the cylinder. Well, in that case, now what I'm going to do is I'm going to draw an Amperian loop like so, with a radius little r. In this case, r is greater, little r is greater than big R. Once again, I have to calculate the current that's enclosed. Well, in this case, it's going to be all of the current. We can sort of shortcut the process. When I want to find the effective current, then I can write that as the integral of j dot dA, and it will be the exact same procedure as before, except I'm going to integrate from 0 to capital R, because I'm encompassing the entire cylinder in this case. So it would be j naught r, 2 pi r dr. And of course, the integral will be exactly the same, except I'm going to replace, in this case, my effective current is going to be 2 pi j naught capital R cubed rather than little r cubed. And that's the only difference. So that will give me the effective current for a point when I'm outside the cylinder. Now when I want to apply Ampere's law, same rule applies. B times 2 pi r, as we had before, is equal to mu naught times 2 pi j naught r cubed over 3. Notice in this case, I have both big R's and little r's, and so I have B is equal to mu naught j naught capital R cubed over 3 little r. And that's going to be the magnetic field outside. Okay? And so that's a really nice example of how to calculate magnetic fields for non-uniform currents. I'd like to do one more example. And this is a little bit more complicated, but it allows us to do one of the nice tricks that we like to do in physics, which is to find where the field is a maximum. So we're kind of going to review the same type of problem we just did, except a slightly more messy looking current distribution. So in this case, we're going to say that J is equal to some constant J naught times little r over r minus little r squared over big R squared for r less than or equal to r. J will be equal to 0 for r greater than r. And again, this is for a very, very long cylinder of radius r. The wrinkle that I want to do in this case is, let's find the magnetic field inside the cylinder and outside the cylinder, but let's also find where the magnetic field is a maximum. So this complicated current distribution will allow us to do that. So first off, same process as before. My effective current is going to be equal to the integral of J dot dA. dA in the case of the cylinder, I'm just going to write as 2 pi r dr. And I'm again drawing my Amperian loop.